Okay, we're going to look at some code this time, do a bit of analysis, because I want to illustrate what we call the Kruskal-Wallis rank sometimes. So sometimes, most of the time we use the standard, methods, the t-test, the ANOVA and all that. And all this assumes, normal data, it assumes constant variance and stuff like that. But occasionally you get situations where you're not happy with that. You want to do something else. And what we call these is non-parametric tests. So as an example of a good non-parametric, we're going to look at the Kruskal-Wallis, which is the non-parametric version of ANOVA. So let's illustrate. We'll load some packages. We'll set the color. And let's just have a quick look at the test that we're going to do. So you're going to use this test when you are worried that you don't have normally distributed data or you don't have constant variance, as I say. So what you do is you calculate, you rank all your observations. So you just rank them in order. How you deal with the where you get two with the same value depends on particular variance of it. But then what you do is you calculate for each group the mean of its ranks. You take off the number of observations, you add times this by the size of each group, and you adjust it. And you're going to get this number H. And then you can use that H to decide whether you reject or retain that the groups have equal means. So as an illustrative example, we're going to look at some data called the air quality data. So let me just have a look. So I've loaded the data. I'm going to convert it into a table and have a look. So what this does is it has a load of observations of air quality over a city. Let's see, it was New York between May and September 1973. What we're going to do is we're going to look at the ozone and see if the ozone changes for each month. So what I'm going to do is I'm going to take this air quality, I'm going to clean these names so they're all lowercase, easier for me to type. We're going to select just the month in the ozone. I'm going to convert, you can see month at the moment is an integer. I want that to be a factor. And also we've got some missing values. So I'm just going to say, if there's any rows that have missing values, just delete them. So what we end up with is just a tibble or data frame, whatever you want to call it. It has 116 rows where each row gives a month and ozone. So this is all May. You can see the first day, 41, 36, etc. So all good to go. So the first thing we'll do is have a look at it. We'll just do side-by-side box plots. And what we see here, if we just zoom in, is there seems to be a difference. We see that if this is May, June, July and August seem to have more ozone compared with the other months. But is there a significant effect of month on ozone levels? Well, that's a simple question to ask. And normally you do ANOVA. But the thing about ANOVA is they should roughly have the same variance. You can see that this month has very little variance compared with, for example, this month. And in fact, if we actually look at the standard deviation, we can see that one month has 39 and another has 18.2. And you might remember the standard rule of thumb is we take the largest, which in this case is 39.7, and you divide it by the smallest, which is 18.2. And if that is greater than 2, then you don't have, as a rule of thumb, constant variance. You can see that this is 2.18. So you could do ANOVA, but you might not get, you shouldn't really do it. The results aren't going to be correct. So what we're going to do is we're going to do the KW test by hand. So first of all, how many observations have we got? So this is N. So let's have a look at N. We've got that 116 we saw before. And what I'm going to do is I'm going to calculate the rank of the ozone, and then I'm going to calculate the mean of the rank, calculate how much in by each group. So let's have a look at this. So if I actually run that and then go ranks, you can see that the average rank of everything in May is 36.7, and there was 26 observations. June, 48.7, there was 9 observations, etc. So now here's the calculation we saw before, all written in R. So if I run that, and I get a H of 29.25. We can use a chi-squared for this. So it's a chi-squared with 4 degrees of freedom because we have 5 levels. So it's basically 5 minus 1, which is 4. We put in the h, we want to do greater than, and we get a really quite small p-value. So we would reject the null hypothesis and say there is a significant difference at the 5% level between these groups. Now, I normally don't do this. I normally don't actually run all this. What I do instead is there is a built-in Kruskal-Wallis test where I can say ozone month and here's the data. If I run that and we have a look, here's the results. You'll notice that the p-value is of a similar level but not quite the same. The test statistic is not quite the same. That's because it depends on how it does the rank. Actually takes care of the ones of equal rank, etc. But there you are, there's a nice illustration. And you'll find that for most of the tests that you will do, you know, the t-test, the z-test, the ANOVA, there is usually a non-parametric equivalent that will use ranks as opposed to the actual values. Why don't we use it all the time? Well, you lose information. Once you convert to ranks, you know, if you were comparing first and second, let's assume that, you know, me and Usain Bolt have a race. And you want to look at the difference between, if you look at ranks, he's going to come first and I'm going to come second. That's the information. But let's face it, he will do it really, really fast and I will do it really, really slow. And you lose all the information about the absolute value of how long we take to do that race. So non-parametric are good in the situations when you can't use the standard test. But if you can use the standard test, they're the best ones to use. Okay, that's it for now. See you next time.